Right. Right. Good afternoon, everybody. For those in the U.S., we're very grateful today to have our next seminar in the U.S. Society for Ecological Economics seminar series. For those of you who don't know me, I'm John Palomeni, the immediate past president, and we have a great presentation today. Karolina Safarzyńska from the Faculty of Economic Sciences at the University of Warsaw. She's done some really interesting research. I've read several of her papers and quite frankly, looking forward to the presentation. And her talk today will be the evolution of tasks, automation, and carbon dioxide emissions. And without further ado, thank you, Carolina.
Thank you. Maybe I will just start briefly by introducing myself. I work at the intersection of few sub-disciplines in economics. I associate myself mostly with complexity economics, but I also work on ecological and environmental economics, which might be seen rival, as well as on behavioral economics. And in my work, I'm studying processes which are deeply embedded in the current economic system and in the society, which can prevent us from achieving sustainable future. The future doesn't look very bright. Doesn't look very bright right now. I don't think many people believe that we will limit global warming to 2 degrees or 1 degree Celsius as we intended to. And we are left with a huge variety of pathways which we are currently exploring. And what puzzled me about this picture is that none of the pathway dioxide emission carbon dioxide emission has been studied under the assumptions that we will have new technologies in place like automation, artificial intelligence, or digital technologies. And also, all those pathways very often ignore metals as constraints for renewable energy, and we know that we will be running some of the metals by 2040. So there is a lot of factors that are not even there in the pictures, and automation and artificial intelligence being one of them catch my interest. And this is why I developed those models to study what will be the energy demand and how it will affect climate change impacts. And this is what I want to present today. I will understand automation as a technology which can reduce labor and energy use in routinized tasks, and artificial intelligence as a form of technology which affects actually cognitive non-routine tasks, which previously we thought were beyond automation. We know something, but so far we know little actually what will be the energy demands in the future. There are some studies showing that automation has reduced energy intensity of the production processes, but we don't know yet whether there will be a rebound effect at the higher scale. And with respect to artificial intelligence, we are expecting that the energy demands related to the huge data centers will be equivalent to adding total electricity use by one of the big European countries, but these are just very early estimates. So I would like to study these effects in macroevolutionary framework. And most of the studies which I've seen so far have focused on the impact of automation on the labor market. And there were few studies, and when I mean few studies, I focus on macroeconomic frameworks, which tackle the issue of the impact of artificial intelligence or AI and automation on energy use on the macro scale. So that's my goals. And to do this, I want to present a hybrid approach, which I developed to study these questions. And this hybrid approach combines 3 different types of models, which is an input-output analysis, the agent-based model of the capital market, and I combine it with a task-based approach to the labor market as developed by Acemoglu and his co-authors. And that's a lot, but in our recent perspective in PNAS, we argue that, which was led by Tatiana Filatova, We argued that to understand climate change issues, it is often, it may be often very helpful to combine different types of models because the challenges we are facing today are very complex and very difficult to understand and how to guide them with advanced climate policy analysis. And what I mean by this is that very often policy instruments like taxes, although needed, they haven't been sufficient so far to guide a structural change needed to achieve sustainability. And not only that I combine different methods, but also this is a combination of a hybrid of a different set of theories. And this will include now Schumpeterian model of growth. The model will be post-Keynesian, meaning that changes in the demand will drive changes in the industry structure and economic growth. I combine input-output analysis and the task-based approach by Acemoglu, which I mentioned. I will just briefly explain it. So he changed the way we are viewing currently production. Before, we were looking at this as a substitution between labor, energy, and capital. And Acemoglu proposes framework where production is seen as a set of or continuum of different tasks which needs to be performed. And my twist to this theory is that I assume that to perform tasks, each firm needs to buy capital, and only through capital, only this capital will define how much labor or fuel the firm will need to perform each task. And a set of tasks needs to be completed for production to take place. The work I will be presenting today is very much related to what I am doing and other people in my field. So we are macroevolutionary community, and we work on developing agent-based integrated assessment models, which essentially can be thought of as we're trying to develop behaviorally rich alternative to integrated assessment models. So an integrated assessment model have these different entities drawn in this graph or figure, represented often by a single equation. Of course, it's a simplification, but I will continue with this assumption for the second. And if they have this aggregate equations which assume rational and representative agents, so what we do, we replace each of them by a network of interacting agents. And moreover, we link it with the detailed representation of the financial sector, which allows us to study financial risk arising from a transition to a low carbon economy. So these sets of models by me and other authors were used to study different types of climate policies. But what was missing was the industry structure. The very early models had actually only two sectors. One was capital producing sector, and the second one was the final good producers. And this capital sector was very important for economic growth because all the innovation take place among capital producers, which I will talk in a second. So there are two ways to introduce, or maybe more, but I want to focus on two ways to introduce industry structure. One is this great achievement by Sebastian Poledna, who created an agent-based model of Austria, where he actually literally modeled everyone there. So he created a model with 8 million agents, which represent consumers and firms, and they all work in different sectors. But this is a very tedious task to model that many interaction or that much interaction. But he was one who introduced the inter-industry structure to those macroevolutionary models. And moreover, it's one of the first agent-based models which proved to be able to forecast macroeconomic growth. We decided that modeling all the industries in such a great detail by having basically all the employees and employers represented from a given country, it's maybe too much since we wanted to model EU. So what we've done is we took the input-output database, in particular Axiobase, which includes 164 sectors, and we aggregated it to two regions, EU and non-EU. And input-output analysis is essentially static. So to bring macroeconomic dynamics, we combine it with capital sector. So essentially, we took the capital sector out of this input-output table, and we assume that each sector has a capital constraint, and if a firm sector cannot produce because it has insufficient capital, it needs to invest in capital goods. And it has a capital stock composed of different vintages, and technological plays occurs as firms add a more productive capital goods to their capital stocks. And on the capital markets, this is this now Schumpeterian way of modeling. We have many heterogeneous capital producers who interact, imitate each other, invest in innovation just to improve the productivity of capital offered to different firms. And we use this model to study, for instance, the impact of the circular economy on the metal markets. And this approach brought the advantage that, on the contrary to other studies, we haven't assumed just that recycling takes place, but it required investment in new capital. So there was this capital constraint. This model showed, for instance, that if one region invests heavily in the circular economy, it can lead to the leakage effect, and actually the copper use can increase as a result of this, which doesn't happen, of course, if globally we introduce a circular economy in many regions. But this is not what I want to talk about. This was the introduction which I made to arrive at this stage where I want to introduce how I combine this approach with the task-based approach to production. So what I've done in the current paper, I took each sector of the input-output table, and I decomposed production in Serene into 23 tasks. And for each task, firms need to invest in capital goods, which will define the productivity of labor and fuel. And I parameterize very carefully the labor requirements per each task. So the sum of all high, medium, and low skill labor across tasks will sum to the labor accounts as we have them in the Excel-based database. And for each of 23 tasks, I calibrated the labor shares for each sector. And this was kind of tedious work, but essentially it relies on taking the ONET database, which is a dictionary describing task intensity of different occupations, then aggregating different occupations across industries and classifying occupations as high, medium, and low skills. And that's the classification of tasks by Echemoglu, where he distinguished non-routine cognitive, routine task, which he classified as cognitive and manual, and non-routine manual. Which allows me now to explain how I model automation. So I assume each time a firm faces a capital constraint, it will invest in a new capital good, and it selects the capital good which will minimize its unit costs. But a firm with certain probability can also purchase a new capital good that actually can replace its entire capital stock by a new capital good, which will reduce its fuel and labor share per unit of output in a given task. And it will only do this if it minimizes its unit costs. And if the automation is successful, a firm buys such a new capital goods, it will reduce its labor share for each labor of type L by this amount, which essentially relies, is proportional depends on the size of the capital good and the productivity of labor or fuel, depending on which labor share of which production factor is reduced as a result of automation. And what we've shown is that here you see carbon dioxide emission in the EU by 2100. And the red line, I'm sorry, the legend is missing, corresponds to automation, and the gray line corresponds to the scenario where we have investment in renewable energy. And this scenario assumes that by 2100, EU invests in that 100% of electricity comes from renewable energy. And the declining lines are just industrial emissions. So what we found is that industrial emissions are reduced the most by automation, but not the total emission. Actually, to reduce total emission, renewable energy, investment in renewable energy are more efficient. But as you see, the total reduction is quite substantial due to automation. I also, since I had such a detailed representation of tasks, I also studied the impact of different types of climate shocks and how they will affect the macroeconomy. And I studied three types of shocks. So there was probability that climate shock destroys firstly capital good, and this probability is increasing with the temperature as well as the size of the shock. And the reduction of the capital stock, which is affected, it's reduced by according to this equation, and it depends on the size of the shock, depends on the temperature and the productivity of capital. Here is capital shock of the size of the capital shock which is affected, and we studied also shocks which reduce labor productivity in cognitive tasks and compare it to the shocks which reduce labor productivity in manual tasks. So here are the results. As you see, if we have shocks to capital, they are very severe for the economy. Oh, sorry, I forgot to mention, the model is also combined with the climate cycle, which was taken from the Nordhaus model. So it is quite simplistic, yet serves the purpose for the study. And all of those three types of shocks will affect macroeconomy through different channels. When you have climate shocks, they reduce production of firms immediately because of the lack of the capital to produce the desired output, but it will also have a secondary effect that will reduce not only production of the affected firms, but also of other firms through the supply chain, according to inter-industrial coefficients of the input-output table. And what the result shows that these effects are very small, but they are significant, that if we have shocks to cognitive labor, it actually is increasing GDP in Europe. And why is that? Is those shocks will reduce reduce productivity of high skill labor the most, but also they have the highest wages. So those shocks will actually reduce the gross wage of high skilled labor, and this way they increase GDP. And when we have shocks to manual labor, they have negative impact on the GDP only outside Europe, but not in Europe. In Europe, the effect is insignificant. And also what I found is that the lack of significance of, for instance, manual shocks is due to the fact that the model includes such a detailed representation of innovation and R&D activities. Because when I run the model with assumption that capital firms don't invest in labor productivity improvements, the reduction of GDP under manual shocks was very strong and significant. So now I want to move to how I modeled the impact of AI on energy demands. There are a few channels through artificial intelligence or diffusion of technology embedding it can affect the energy use in the economy. First, of course, is direct effect on the ICT sector. Second, it will enhance productivity mostly of high skill labor, which will drive economic growth, and both of these effects can increase energy use. But there will be also some sectoral changes and efficiency improvements which can mitigate these effects. But so far the literature has not concluded what would be the overall effect, but we are expecting it will be still positive on energy use. There are some studies which tackle the question of how much energy use will increase as a result of AI, but they tackle one of these mechanisms at the time. So I wanted to study to disentangle these effects using the model I'm proposing. So one of the important property of this model is that I assume that artificial intelligence will affect cognitive skills in the long term. There are some discussion that this impact probably will be negative. There are authors who says that relying on technology will lead to cognitive offloading or metacognitive laziness. The people rely too much on cognitive effort. To some extent, this is true, but mostly occurs maybe in routine cognitive tasks, which we can automate. But AI also expands, in my view, boundaries of knowledge. It enables analysis of large data sets that previously could not have been studied due to insufficient computational power. And in the long run, probably it will lead to the emergence of new tools and methods that requires complex skills. So these are the mechanisms which I would like to conceptualize. So to do this, I modify the model which I've just presented, that I distinguish different types of capital producers. So those who specialize in producing capital goods for manual tasks, they will still work on improving labor, fuel, and capital productivity. But those who produce capital goods for cognitive tasks will improve the productivity of capital and fuel as before, but instead of improving labor productivity, they will work on easing the task difficulty with which different tasks are performed. And as a result of this, the productivity of labor and this is of labor L, employed in task K, in industry I, using capital good C, will depend on the skill of associated labor employed in this industry using this particular capital good. And here we have this task difficulty. And I assume that capital firms which embed AI into the product, they will make the product more difficult, contrary to other firms which will ease the task difficulty. So if the firm is easing task difficulty, this will improve labor productivity. But when we have capital goods which embed artificial intelligence, they will have higher task difficulty, but this will increase the maximum attainable skills in the economy, and also will have the impact that it will require more electricity use. The second assumption that it will affect the maximum skills in the macroeconomy is very important because it helps to conceptualize the stylized facts from the literature that actually the diffusion of AI leads to this J paradox, that at first is reducing the productivity of firms using artificial intelligence for the work, and only in the long run is improving it. So to conceptualize those mechanisms in the model, skills are evolving according to those two components. One captures relative task difficulty, and here the assumption is that if a firm buys capital good which requires lower, which is easier than skills of labor which it currently has, it will lead to the deterioration of skills by labor. And the second component is like some captures the learning effect, that in economy skills are catching up with maximum attainable skills. So the strengths of this effect I will measure. I will examine how the strengths of this effect will affect macroeconomic dynamics, and beta is the I will call learning rate. And just to close all this description of the assumptions, here is the energy productivity of capital goods embodying AI, and it is equal to it's drawn from some range as energy efficiency of other capital goods, but then it is reduced depending on the task difficulty. So this way, I capture the assumption that such technology requires more electricity to perform. And the maximum attainable skills will also be linked to the task difficulty. So the more difficult task is, the higher the maximum skills labor can achieve by using it. And the last assumption which I wanted to mention is that in the scenario where firms consider whether to purchase capital goods and that embed AI, there is a probability that firm will consider such capital goods. Otherwise, it's choosing capital goods which is minimizing its unit production costs. And the probability that it is industry specific, and it's based on the AI industry exposure scores by Felten, which were adapted for the purpose of this study. And here are the results. So here we have three scenarios for different beta, which is the learning rate, with the possibility of firms purchasing capital goods embedding AI. It's here, and when it's a base, and I compare it to the baseline where firms don't have this possibility. So what we see is that AI is increasing the skill inequality. It will actually increase the mean skills, but I don't think I have the picture, but also it will heavily increase skill inequality in the economy. Whether it will increase the GDP, it will depend on the strength of the learning effect. If it's very low, the benefits, the productivity gains of AI are very low. Although, as you see, in general, the GDP growth will be higher. But if the beta is high, we have a very high high gains from AI in terms of GDP, and also which will increase the CO2 emissions. So then what I wanted to do was to decompose this and electricity demands of AI between two effects. One is direct use due to the diffusion of energy in efficient technology, let's say, and second is through those productivity gains brought by AI. And what happens when we have very low beta? Most effects is related to the direct effect. But when we have high beta, about 50% is coming from the direct effect and about 50% from indirect effect. And to conclude this, I ran additional simulation where I had no energy efficiency reduction related to AI. And here are the results. So here, this amount of electricity used is related to the productivity gains. And what the model predicts is that if the learning effects are strong, as we can expect in the European economy, we can expect that our electricity demands of AI will quadruple by the end of the century. And this is despite of the fact that firms which produce capital goods embedding AI will also improve its energy efficiency over time. So there is this assumption in the model. And I will finish here. I wanted to show that the combination of different types of models can be useful for addressing questions related to climate change and energy use. And I'm very much looking forward to the discussion. Thank you.
Thank you, Karolina. That was excellent, very interesting. So we're going to open it to questions and comments. If you would like to ask any, just raise your hand or put it in the chat. Alex, I see you put something in the chat if you'd like to go ahead.
Oh, that was from before Karolina started her presentation, just saying.
I'm sorry, I just saw it.
But I can kick us off with kind of a fun question, and that is, I'm curious if and for what you used AI for this study, Karolina.
Sorry, I didn't get the questions. Can you?
If you used AI for this study and for what purposes?
No,
No?
I haven't.
Nice.
I haven't. That's an old-fashioned style of modeling.
Is there any other questions or comments? So one of the things I'll go while people think of something. So obviously AI is the new thing and it's fancy and all that. And that's looks to be our future, but you brought up the major concern with the energy consumption and the needs of AI. So much so that they're even thinking of like modular nuclear plants solely for an AI factory. Um, so based on your results, I mean, what are your thoughts about AI systems and moving forward um, in terms of everything you've done with productivity and the energy consumption? What are your thoughts based on your results?
Well, I think that the energy demands will be substantial, uh, but there's much like we should start thinking about it. Of course, a lot of people are doing this, but how to mitigate the impacts? And of course, investment in renewable energy is one of them. But we know also that that cannot be the entire solution. Like we cannot green the entire electricity system. Every time we invest in renewable energy, we need to use still fossil fuels. It's a much more complicated picture. There's some multiplier effects. And this was also one of the motivation to do this study. And so, yes, but I was also interested in this cognitive performance, which is very important, and it will have a positive impact, and it will increase economic growth, in my view, and in view of many others, uh, which will again increase energy demand. So it's like we are always uh, struggling to keep up with the recent developments, but we are constantly so far increasing our energy use. And although there's so much hope that we will reduce it because AI will help us optimize the production processes. The scale of this, maybe it's not sufficient to reduce energy use in the future. That's my intuition based on the model I was doing.
Uh, I agree with you. It's very interesting. Yeah, I liked what you presented. So thank you. Um, in terms of the model itself, um, one of the things I think is interesting with energy is the climate change aspect, which you kind of touch on a little bit. But did you incorporate that in as a variable in the sense of and what I mean by that, like increased heat, colder temperatures, so that adds to the aspect of um, energy consumption and environmental degradation. So, is that something that you put into the model or thinking about down the line with maybe a social accounting matrix?
I was thinking about the social accounting metrics. It's not there in the model. No, it's a simplified climate cycle based on Nordhaus. So we have the temperature, which is related to energy use. There's in the Axio base, there's a lot of different energy sources. So each of them has a coefficient related to its carbon intensity. Uh, sorry, like I forgot the question. What
Just
explaining of
incorporating climate change as almost like an endogenous variable.
yes, it is endogenous to the model,
All
but
right.
it's still simplistic compared to what people are currently doing with multiple climate tipping points, climate damages, stochastic, deterministic. Yes, this model doesn't include this.
Um, looks like everybody's got to go. So one more question is related to your future work. Where do you, because I do think what you have is quite interesting. Where do you plan on taking this to the next level?
I'm currently working on the project on the model, which will be actually done using agent-based model, not the input-output table. So we are going to end making all the industries with a lot of agents, maybe not as the scale as Sebastian Poledna, which I was describing. And I'm studying the social tipping points in relation to multiple climate tipping points. So that's the plan for the next research.
Oh, great. Interesting. Um, any other questions? A lot of people had to run. Bad time of year. Final exams in the US. Do you have any last comments you'd like to make?
No, thank you. Thank you for having me here.
No, no, thank you. Like I said, I found your research quite interesting and really want to thank you for taking time out of your schedule to do this for us, especially as we head towards Christmas. And really appreciate it and look forward to reading more of your research and seeing that. So thank you so much.
Thank you.
Thanks. Bye,
Bye.
everyone.